Question tells me that I'm dealing with a Poisson distribution. In English they say Poisson, in French it's Poisson. And the important thing is I've got 5.3 people per hour, which means that my distribution is Poisson with the parameter 5.3. I want to know that exactly 7 patients arrive in at 1 hour, and your calculator will do this for you, but it is a good idea for you to write something along these lines. The probability that x equals 7 is given by e to the minus lambda, in this case 5.3, lambda to the r, 5.3 to the power 7 over 7 factorial. Which will give us a calculated answer of 0.1163428763. Part of the difficulty we've got is that calculators are too accurate. So I would say 4 decimal places would be a reasonable degree of accuracy. If you're going to use your trusty calculator, then it is menu 7, downward arrow, Poisson PD, variable, and you're going to use x equals 7, lambda equals 5.3. Remember, to use the calculator you have to press the equals after each of them, and you will also get that particular probability to exactly the same number of decimal places. Therefore it'll give you the same answer. So really simple, really straightforward. Now, in this particular case, and this is common with exam questions, they've changed the time scale. Right, it's a 90-minute interval, therefore you're going to have to change your parameter, and we want it to be less than 0.09. Okay, so we're looking for our probability for something to occur to be less than 0.09. Now, doing my bestest sums, I know that 90 minutes is 1.5 hours. Okay, so therefore my parameter in this particular case is going to be the 5.3 I had before multiplied by 1.5, which will give me a 7.95. Now, what's interesting to note, so x is Poisson with parameter 7.95, that neither of these questions will allow you to use the standard tables. You're going to have to use a calculator, and that's okay. So I'm going to use a calculator, but this time I'm using a Poisson CD, because it's a cumulative distribution. It gives me the probability, so I'm going to start at a reasonable number. I'm looking for a very small probability, so it would seem fair to me that I don't want to be starting with, I've got 5.3 in 1 hour. If I go for 10, that's not unreasonable. It will give me too big a probability. I'm looking for something quite small. So I know that I'm looking for something reasonably big. Now remember that the calculator gives you probabilities less than or equal to. So I'm going to choose to look at 11 first of all. And using my trusty calculator, so menu 7, downward arrow Poisson CD, 2 for the variables, and I'm going to put in x equals 11, lambda equals 7.95, and my trusty calculator gives me a very, very long number, 8916516632. But the implication of that is the probability that x is greater than or equal to 12 is greater than the 0.09 that I require. So I'm going to move on to the next one, and in fact you don't have to put the whole lot in again. You can just press the equals again. So the probability that x is less than or equal to 12. So I just have to change the x to 12. My parameter stays the same. Press the equals again. This gives me 0.9385791301. And clearly the remaining probability, the probability that x is greater than or equal to 13, is going to be 1 minus that 0.938579 squiggly bits, 1301. I'd love to know why that does that. It's something to do with the controls on this keyboard, but hey. And therefore the probability that x is greater than or equal to 13 is less than 0.09. Therefore my result is n is equal to 13. Now, so in this particular case I only need one reason. It's only got to be fairly simple. And if you want a Poisson model, then you have to be able to show two elements. One is that the items are independent, and secondly, they occur at a constant rate. Now, you've only got to think of one reason as to why that wouldn't be the case. If you've ever had the misfortune to be in a A&E department on a Saturday evening, you know that it's a lot busier than other times of the week. So you get busy periods and you get slack periods. So it's not a particularly good model. The other thing, of course, to consider is that it needs to be independent. That is, the probability of one patient arriving is completely independent of another patient arriving, which, given that road traffic collisions, major incidents occur, that's not the case, because then ambulances transport more than one patient at a time, and therefore you're stopping that independence. So you need to have a reason of that nature, but you would need to write that. And given that I'm trying to produce a bilingual presentation, my colleague is going to do a Welsh overdub of this as well, then we're not going to actually write any words in this, but you would need to write bullet points would do. That's fine.
A quick look at what the Poisson looks like and a thought about the final part of the question. The Poisson with small values of lambda is very much skewed to the right, or skewed positively. But as we increase lambda, the skew becomes less. By the time we get to 5.3, which was in the question, it's reasonably symmetrical. It's still a bit skewed. Now, the reasons given for the Poisson possibly not being appropriate in this case were firstly that sometimes might be busier than other times, so the classic Friday night at A&E when people have been overindulging, and also that the occurrences may not be independent. So the example given, if there's a car accident, you may get several casualties arriving at once and they are all related to each other. One way of overcoming this, if you wanted to still use a Poisson, is, for example, to use a period of a week. And for this, we could multiply the hourly rate by 168, which would give a great big Poisson, but nevertheless would make some sense. If we think about evening it out over a day, which would perhaps smooth out some of the problems with it not being properly random or independent, looking at it over a whole day, then that's 24 hours. So 5.3 times 24 is about 130. So I'll have to do a couple of quick things. First of all, slider was set up only to go up to 40, so we'll change that to 140. And now we can slide that up to around 130. Only has to be rough for looking at it like this. There we are. That'll do. Okay, so off it's gone over here. Get there in the end. And we could actually zoom. Now you can see that the spread of it is much wider. It's become very symmetrical. If we change the zoom a little bit, could we risk 500? Don't know if it'll fit. Oh, beautiful. So that looks very symmetrical. One thing I want to mention here is a couple of things, one of which all of you pretty much will be studying in Mathematics A2, and the other that some of you will study in further maths, or may have studied already. And they are the normal distribution, which comes up in A2 statistics, and approximating distributions to other distributions, which comes up in further maths. So in particular to this situation, if we put the normal distribution on top of that curve, we can see that it's very similar in shape. The Poisson is a discrete distribution in that values can only take whole numbers. You can't have half a patient coming to a hospital. And the normal distribution is continuous, so it can take any value. But nonetheless, you can see the shape of the distributions is very similar, and so we can use the normal distribution as an approximation to the Poisson. And there are various advantages in that. So those were just a few thoughts on the appropriateness of a distribution. So looking at the idea of using the mean over a different time period, which could make it a more reasonable distribution to use. Approximating distributions, which will come up in further maths, and a little look at the normal distribution, which will come up for you in A2.